Hello everybody, in this video I will talk about Lagrange multipliers and we will start with a question to this subject. The question is that a rectangular box without a lid is to be made from 12 square meter of cardboard and we want to find the maximum volume of such a box. And to do this, first of all, I will draw the box here, and this box will be something like that. We have a rectangular box, okay, here. And these are the sides of this box. Okay, so let the length, width, and height of this box in meters be x, y, and z. This is length, and this is width, and this is height of this box. And then if you call those sides like that, then the volume of this box will be v x times y times z. All we know this rule, right? And then now we can express v, this volume, as a function of two variables. As you can see here, we have three variables, x, y, and z. But we know to find the absolute maximum and minimum of a function of two variables using second derivative test. So we can make this function two variables using the fact that the area of the four sides on the bottom of the box is 12 square meter, right? And this is given in the question. And we will use this information. And because this box made from the 12 square meter cardboard, it means the area, the total area of the box will be equal to 12. And don't forget this is an open box. There is no area at top. Okay, so the area will be, first of all, we have a bottom area which is xy, plus we have two sides here, x times z, this side is z, 2xz, plus here we have a yz, 2 times, and this equals 12. There is no any other area here. Okay, so I can leave z alone, which means I can solve this equation for z, and then the obtained result can be substituted here. Then this v, the function v, volume function, will depend on only x and y. Okay, so let's solve this equation for z. Here I have in the common parentheses of z 2x plus 2y, and I will take this term to this side, 12 minus xy. And at the end, z equals 12 minus xy over 2x plus 2y. Or this can be rewritten like that. 12 minus xy over, in the common parentheses of 2x plus y. Okay. Now, I have this result for z, so the expression for v turns to, here as a result, v becomes x times y times this z, 12 minus xy over 2x plus y. Okay, so as you can see now, we have a function depends on just two variables. So it means I can use the idea, the known idea for the absolute value to finding the absolute extrema of two variable functions here. And to do this, I will first of all find the critical points of this function. And first of all, we will evaluate the partial derivatives of this function. And derivative of this v with respect to x will be, please calculate it on your own. The result will be y squared times 12 minus 2xy minus x squared over, in the common parentheses of 2x plus y squared. Okay, and the derivative of this v with respect to y will be equal to x squared times 12 minus 2xy minus y squared over in the common parentheses of 2x plus y squared. Okay, so if v is a maximum, then we know that this occurs at the critical point or at the end points. Okay, but here the end points mean one of x or y, one of x or y is 0 here. Okay, so if x is 0 or y is 0, volume will be 0. So this can't be a maximum value. So because of that, we will look for the critical points. And to obtain critical points, we will equate those partial derivatives to 0. Okay, so let's try to obtain the critical points here. Del v over del x equals 0. Okay, means y squared 12 minus 2xy minus x squared over 2x plus y squared equals 0. And it says that y is 0 or 12 minus 2xy minus x squared 0. And we have a similar result from the second partial derivative here. X squared 12 minus 2xy minus y squared here over 2 times x plus y squared is 0. So I have x is 0 or 12 minus 2xy minus y squared is 0. Okay. But as I said, if x is 0 or y is 0, volume will be directly 0, right? So because of that, at these points, we won't have a maximum volume. So we won't deal with x is 0 and y is 0 here. Let's try to solve the other equations. Let me write it here. If x is 0 or y is 0, then volume will be 0. So this can't be maximum. If it is not maximum, so we should solve the other equations, which means we will deal with those equations. Okay, 12 minus 2xy minus x squared is 0, and 12 minus 2xy minus y squared equals 0. Okay. So as you can see here, these terms and these terms are equal, right? So I have such those equalities. 12 minus 2xy equals x squared. 12 minus 2xy equals y squared. So it says that x squared equals y squared. So x equals y. We won't take x equals minus y because we know that x, y, and z are lengths, so that they should be positive here. Okay, so we have only one choice, which is x equals y. And here, if we put x equals y in either equation, then we will obtain this result. Substitute this here. Okay, I will substitute this in the original equations. 12 minus 2 x times x minus x squared equals 0, which means 12 minus 3x squared equals 0. So I have 4 equals x squared, so x is 2 here. Again, as I said, x cannot be equal to minus 2. Let me write it here since x is length here. Okay. So if x is 2, we know that x equals y. Because of that, y will be 2. Okay, so when x2 and y2, z will be equal to, we know the formula for z here, 12 minus xy over 2 x plus y. 12 minus 2 times 2 over 2 times 2 plus 2, which means I have 8 over 8 here, so which is 1. So as you can see, we obtained the critical point. So critical point is 2, 2, 1. So we have only one critical point. It means we have the maximum value at that point. The absolute maximum of vxy occurs when x is 2, y is 2, and z is 2. So the maximum value of the volume is 2 times 2 times 1, which is 4. Okay. So in this problem, we maximized a volume function v which equals x times y times z, subject to the constraint 2xz plus 2yz plus xy equals 12, which expressed the side condition that the surface area was 12 meters square. So here, function to be optimized is volume function. We just try to find the maximum value of this function. And here constraint is 2xz plus 2yz plus xy equals 12. Okay, so, and this defines the area, surface area. Okay, and the surface area should be equal to 12 here. So in this section, we present Lagrange methods for maximizing or minimizing the general function f of x, y, z, subject to a constraint of the form, or two constraints of the form g of x, y, z equals k. Okay, if you can't, like here, if you can't solve one of the independent variables in terms of the other, you can't use this substitution method here. We solve that in terms of x and y, then we can substitute it here. But if you can't obtain just the function, like a function, then you can't substitute that here, right? So you can't obtain two variable functions. So because of that, you will need another method here. And we will call this method Lagrange multipliers. And to understand what is the Lagrange multipliers, first of all, I will explain the geometric basis of these methods for functions of two variables. Then we will talk about the general case. So we start by trying to find the extreme values of f of xy. Here we are looking for the extreme values of extreme values of f of xy. Okay, and here the constraint function, here the constraint function is g of xy equals k. Okay, so we are looking for the extreme values of f of xy subject to a constraint of the form g of xy equals k. In other words, we seek the extreme values of f of xy when the point xy is restricted to lie on the level curve g of xy. Here, this is the level curve g of xy equals k. Okay, this is just a level curve, one of the level curves of this function, but here the value of this level curve is k. And this figure shows this curve together with several level curves, actually four level curves of f. And these have the equations f of xy equals c, as you can see, but c is 8, 9, 10, and 11. This is just an example, okay? And to maximize f, this function, subject to that constraint, is to find the largest value of c, this c, the largest value of f of xy equals c, such that the level curve f of xy, one of those level curves here, intersects g of xy equals k. Okay, so it appears from the figure that this happens when these curves just touch each other. In other words, they have a common tangent line here. Okay, there is a common tangent line. So the maximum value of this function subject to that constraint occurs when this level curve and the level curve of f has a common tangent line. Why? Otherwise, as you can see, the value of c could be increased further. For example, if you look at that level curve, yes, we have two intersection points. But if I increase this c as 9, still I have two intersection points. But if I increase 9 as 10, then at the end I have a tangent line here, and I can't increase 10 one more time, because if I choose the C as 11, there is no intersection point here with g of xy. Okay, so we should look for the point at which it is in the tangent lines of g of xy and f of xy at the same time. This is a common tangent line. Okay, so this means that because the tangent line is common here, the normal lines at the point, if I call this point x0 and y0, the normal line at this point has the same direction vector. Okay. Normal lines at the point x0, y0 where they touch are identical. So the gradient vectors are parallel. Why? Because we know that the normal line of the direction vector of the tangent line here, direction vector of the normal line of a curve is equal to gradient vector of that curve, right? So because of that, because here this curve and this function has the same tangent line, they have same gradients at that point. So because of that, we have the a relation between those gradients, which is which that they are parallel to each other. I will summarize it like that: gradient of f at this point equals lambda. This is just a constant here. Because they are parallel to each other, they should be a constant multiple of the one of them is a constant multiple of the other. Okay, so here for some scalar lambda, so we have a function to be optimized and we have a constraint function, and we decide that this maximum point or the minimum point, the extreme value occurs when this function and this function touch each other at just one point, which means they have a common tangent line. If they have common tangent line, they have normal lines at the point where they touch identical here. They have same normal lines. Okay, normal lines are parallel to each other, which means the gradient vectors, which are the direction vectors of those normal lines, parallel to each other, and because they are parallel, they should be, one of them should be a constant multiple of the other. Okay, and the number here, the number lambda, is called a Lagrange multiplier. Okay, this part is related with the two variable case, and I will give the method of the Lagrange multipliers for the general case, in other words, for the three variables case here. So to find a maximum and minimum values of f of x, y, z, the function of three variables, subject to a constraint function. Here, this is the function we want to maximize or minimize, and this is the function which gives the side condition here, the constraints. And of course here we assume that these extreme values exist and the gradient of g is different from 0 on the surface. Okay, so we will follow those steps. First of all, we will find all values of x, y, z and lambda such that this equation satisfied. Okay, g of x, y, z and g of x, y, z equals k. Okay, we have two equations and we are looking for the points x, y, z and lambda which satisfy both of them at the same time. And then we will evaluate f at all points we obtained in step 1. Then the largest of these values is the maximum value of the function, and the minimum and the smallest value is the minimum value of the function. So using these steps, we can obtain maximum or minimum values of a function subject to a constraints. Okay, we are looking for the extreme values of f, but we also want that those points x, y, z at which the f takes its extreme values also satisfy this equation. So because of that, this equation is called constraint of this function for this time. So to solve, to obtain maximum and minimum values of this function subject to that constraint, first of all, we should solve the equation, the gradient f equals lambda gradient g and this constraint at the same time. And then we will substitute those points at f and we will obtain some results. Then comparing this result, we can decide that the largest of these values is the maximum value of f and the smallest is the minimum value of f here. So this method is called Lagrange multipliers, and this is the end of this video, and we will solve some problems in the next video. See you on next video.